In the previous video, What is a Capacitor Part 1, we explained how a capacitor stores charge, we presented an equation for capacitance, and we talked about breakdown voltage. Now I want to examine the current into a capacitor versus the voltage across the capacitor. Let's presume we have a capacitor and the bottom plate is tied to ground, and the top plate is connected to a current source, which I'll draw as a box with an arrow indicating the direction of the current. And let's presume that we have 1 amp of current for 1 second. And after 1 second, we'll shut down the current and have no current flowing. And let's presume we have a 1 farad capacitor, which 1 farad is really a large capacitor and not used very often. A more common capacitance may be picofarads, which is 10 to the minus 12th power, or very, very small compared to a farad. So just be aware that a farad is a very large capacitor, but in our calculation here, it's just fine. So let's plot this current. At time, initially we start with 0 current, and at some time we ramp up to 1 amp of current, and it stays 1 amp for 1 second, and comes back to 0. So here's a graph of time in this axis, and in this axis we have current, and here we have 1 amp and 0 amps. And let me label this point here 1 second. Now we know that the charge in the capacitor is equal to the capacitance, which in this case is 1 farad, times the voltage across the capacitor. So solving for voltage, we can say the voltage is equal to the charge divided by the capacitance. So let's try to determine the voltage across the capacitor. So let's say at this time we're going to plot the voltage, and let's make a time axis. So this is time in this direction, and initially we start out with 0 volts across the capacitor and no current through it. So initially we start at this point, 0 volts at this instant in time. So we're plotting current versus time. The area under this current pulse is actually charge. And if we have 1 amp for 1 second, we have 1 coulomb. 1 coulomb of charge, which is just the area under that curve. So let's say at this point in time right here, we have a voltage that depends upon the amount of charge. Let me change colors here. Amount of charge in this section here. And a little later time, we've increased the charge on the capacitor. And finally, at 1 second, we're at this point. So the voltage ramps up in a linear fashion. Then when the current goes away, the voltage across the capacitor just remains constant. So let's say at this point, if this is a 1 farad capacitor and we're putting 1 coulomb, we'll have 1 volt across the capacitor. Let's consider if our capacitor was a little larger. Instead of saying that's 1 farad, Let's make it 2 farads. What's going to happen to this voltage versus time curve? What's going to happen is the denominator is bigger. It's now twice as big. So the voltage is going to be decreased. It's still going to ramp up in a linear fashion, but it's going to only get to a half a volt, and then it levels off and stays constant. Let me erase this. Now let's think about what we can do with the capacitor. Now we know that the voltage across the capacitor is equal to the charge put into the capacitor divided by the capacitance. So we can say that the change in voltage, which I'll call delta, is proportional to the change in charge in the capacitor, which I'll call delta Q. So a capacitor tends to resist a change in voltage. For the voltage to change, it takes time for the charge to change. And if we want a very small voltage change, we could have a big capacitor. So a big capacitor in the denominator makes a change in voltage small. So very often in power supplies, for example, if we have say we have a 5-volt power supply, you may see in a schematic, you may see a big capacitor across this power supply and tied to ground. And what this capacitor does is it smooths out the power supply. If you have noise on your power supply, the capacitor will hold the charge there. It'll hold the 5 volts. And if the capacitor is very big, and remember C in the denominator will make the change in voltage very small. So if we have a very big capacitor, then it'll hold the voltage better. So for example, we may have a load out here attached to this power supply to ground. Maybe this is a clock or a radio. And even if our power cut off instantly just for a short time, this capacitor would try to hold the voltage there, and it would discharge rather quickly, but for a very short time it could help to hold the charge there. And notice that I drew the bottom plate of the capacitor with a curve. That's sometimes done with a capacitor that has a polarity, where this is the plus terminal of the capacitor and this is the minus terminal. And for very large capacitors, very often they'll have a polarity. It'll be an electrolytic capacitor. And the plus side of the capacitor must connect to the high voltage side, in this case the 5 volts. If you reverse the polarity on the capacitor, it could destroy the capacitor, and it's not a good thing to do. So let's examine another thing we can do with a capacitor. We can use it as a filter. For example, if we have a resistor and a capacitor, I'll draw the capacitor to ground. And let's say that we have a little bit of noise on this input to this resistor. And here I'm plotting time and voltage in this axis. So we have a little bit of voltage fluctuation for a short amount of time. Now, the capacitor will tend to resist change in voltage. So the capacitor tries to hold this voltage at this point constant, and this resistor R limits the amount of current that can flow into the capacitor. So the voltage seen here will be attenuated. It'll be a lot smaller. So the capacitor can be used in conjunction with other components to form a filter. In this case, the capacitor is filtering out noise at the input, and reducing it here at the output. We could also use this filter to eliminate very high frequencies at the input. If we had a very high frequency waveform, this capacitor will look almost like a short circuit, and the frequency here will be greatly reduced at a very high frequency. Now let's examine something kind of far out that you could do with a capacitor. Let's take a capacitor and let's ground the bottom plate, and we know a capacitor stores charge, but I'm going to use this capacitor to model my retirement savings account. Instead of storing charge, I'm going to have it store my money for retirement. Now, how could you do that? The capacitor stores electrons. Well, make an analogy. Let's say that I have a current flowing into this capacitor, and let's presume I have a 1 amp, which is a coulomb per second. So we have 1 coulomb of charge every second flowing into this capacitor. A coulomb of charge, let's say, corresponds to $1,000 in my savings account. So we say 1 coulomb equals, in terms of money, $1,000. Now, if I have an amp, let's pretend that 1 second is equal to 1 month. So what I'm modeling here is every second, in this case every month, I'm putting $1,000 into my savings account. And I can monitor, there are simulation programs that I can monitor the voltage across this capacitor versus time. So if we plot the voltage versus time, I can see my savings growing. And after 12 months or 12 seconds of simulation time, I should have 12 volts across my capacitor. So all I have to do is read the voltage across the capacitor, and I know what I have in my savings account. At this time, at 6 months, I have $6,000. Here I have $12,000. If I stop saving, it's going to stay flat, and I start saving and it'll ramp up again. And I can also add another circuit component, and I can model the interest rate that my savings account would get. And so there's really no limit to what you can do with a capacitor, or almost no limit.